Everything you can see, every star, every planet, every galaxy, every atom in your body represents only 15% of the matter in the universe. The other 85% is invisible. It doesn't emit light, it doesn't absorb light, it doesn't interact with electromagnetic radiation in any detectable way. We call it dark matter. You're surrounded by it right now. Dark matter particles are passing through your body at this very moment, millions of them every second. They pass through the entire Earth as if it weren't there. We've never directly detected a single dark matter particle. We don't know what it's made of. We don't know its properties beyond its gravitational effects. Yet, without dark matter, galaxies wouldn't exist. Stars wouldn't have formed. You wouldn't be here. Dark matter shapes cosmic structure on the largest scales. It holds galaxies together. It bends light from distant objects. It leaves gravitational fingerprints in the cosmic microwave background radiation. We know dark matter exists with absolute certainty. The evidence is overwhelming, undeniable, measured in dozens of independent ways. But we don't know what it is. Particle physicists have searched for 40 years. They've built detectors deep underground to shield from cosmic rays. They've created the world's most sensitive instruments, cooled to near absolute zero, waiting for the faintest signal of a dark matter collision. Nothing. The Large Hadron Collider has smashed particles together trillions of times, searching for dark matter production in high-energy collisions. Nothing. Space telescopes have mapped dark matter's distribution across the universe using gravitational lensing, the bending of light around massive objects. The maps are detailed, precise, beautiful. But they only show us where dark matter is, not what it is. Today, we explore the invisible universe. We trace the history of dark matter's discovery. We examine the evidence that proves it exists. And we confront the uncomfortable reality that the vast majority of matter in the universe remains completely unknown to us. In 1933, Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a group of over 1,000 galaxies located 320 million light-years from Earth. Zwicky measured the velocities of galaxies in the cluster by analyzing their Doppler shifts. Galaxies moving toward us appear blue-shifted. Those moving away appear red-shifted. From these velocities, he calculated how fast the cluster was rotating and how much mass would be needed to hold it together gravitationally. The result shocked him. The galaxies were moving far too fast. At those velocities, the cluster should have torn itself apart long ago. The gravity from visible matter, stars and gas, was insufficient by a factor of about 400. Either the galaxies would escape, or there was additional mass, unseen mass, providing the necessary gravity. Zwicky called this unseen mass dunkle materia, dark matter. His contemporaries dismissed the finding. Measurement errors, they said, or perhaps galaxies contained more dim stars than estimated. The idea of invisible matter dominating the universe seemed absurd. For decades, Zwicky's discovery was largely ignored. In the 1970s, astronomer Vera Rubin was studying spiral galaxies, measuring how fast stars orbit at different distances from galactic centers. Newtonian gravity makes clear predictions. In the solar system, Mercury orbits faster than Earth, which orbits faster than Jupiter. Velocity decreases with distance from the Sun, following Kepler's laws. Galaxies should behave similarly. Stars near the galactic center should orbit faster than stars in the outer regions. Rubin measured rotation curves for dozens of galaxies, working with Keb Ford using sensitive spectrographs at Kitt Peak and Lowell Observatory. What they found contradicted expectations completely. Stars in the outer regions of galaxies, far from the galactic center, moved just as fast as stars closer in. The rotation curves were flat, not declining. This meant the mass distribution didn't match the light distribution. Visible matter concentrated near galactic centers, but total mass extended far beyond. There had to be vast halos of invisible matter surrounding galaxies, extending well beyond the visible disk. Rubin's observations couldn't be explained away. They were too consistent, too well measured, replicated across too many galaxies. Something invisible was holding galaxies together. By the 1980s, evidence for dark matter had accumulated to the point where cosmologists incorporated it into the standard model of cosmology. The lambda CDM model, lambda representing dark energy, CDM representing cold dark matter, became the framework for understanding cosmic structure. Cold means the dark matter particles move slowly compared to the speed of light. This is important because slow-moving, cold, dark matter clumps together under gravity, forming the scaffolding where galaxies can form. If dark matter were hot, moving near light speed, it would be too energetic to clump, and structure formation would proceed differently. Observations favor cold dark matter. Simulations using CDM reproduced the observed distribution of galaxies, galaxy clusters, and cosmic web structure remarkably well. The model makes specific predictions. Number 1, dark matter comprises about 27% of the universe's total energy density. Number 2, normal matter, baryonic, comprises about 5%. Number 3, dark energy comprises about 68%. These numbers come from multiple independent measurements: cosmic microwave background observations, galaxy surveys, supernova distances, gravitational lensing studies. All agree the universe is dominated by components we don't understand: dark matter and dark energy. Before exploring what dark matter might be, let's eliminate what it isn't. It's not ordinary matter that's dark. MASHOs, massive, compact halo objects, like brown dwarfs, black holes, or neutron stars, were early candidates. These objects don't emit much light, but have mass. Surveys searched for MASHOs using gravitational microlensing. When a massive object passes in front of a background star, its gravity bends light, causing temporary brightening. Results? MASHOs exist, but they contribute less than 20% of the required dark matter mass. They can't explain galactic rotation curves or cluster dynamics. It's not gas or dust. X-ray observations detect hot gas in galactic clusters. Radio observations detect cold gas. Infrared observations detect dust. All contribute to baryonic matter budget, but not enough. The missing mass remains missing. It's not modified gravity. MOND, modified Newtonian dynamics, and similar theories propose that gravity behaves differently at low accelerations, eliminating the need for dark matter. MOND can fit some galactic rotation curves, but it fails to explain the bullet cluster collision, discussed later, cosmic microwave background anisotropies, large-scale structure formation, and gravitational lensing observations. Modified gravity theories struggle with the full range of observations. Dark matter, despite being unknown, fits everything. It has to be something new, a particle or field not yet discovered.
In 2006, observations of galaxy cluster 1E0657-56, nicknamed the Bullet Cluster, provided the most direct evidence for dark matter. Two galaxy clusters had collided at speeds around 4,700 kilometers per second. The collision happened about 150 million years ago. We're seeing the aftermath. During the collision, the gas from both clusters interacted. Hot intracluster gas, visible in X-rays, slowed down through electromagnetic forces and pressure. It now sits between the two clusters. The galaxies barely interacted. Galaxies are mostly empty space. They passed through each other like ghosts. The dark matter also barely interacted. It passed through the collision zone, following the galaxies. Gravitational lensing maps showed where mass was concentrated. The lensing signal, the bending of light from background galaxies, didn't align with the X-ray gas. Mass concentrated where the galaxies were, not where the visible matter, gas, was. This separation of mass from visible matter is exactly what dark matter predicts and extremely difficult to explain with modified gravity. The Bullet Cluster provided a smoking gun, direct observational proof that mass and light can be in different locations, requiring unseen matter. The cosmic microwave background, or CMB, light from 380,000 years after the Big Bang, encodes information about dark matter in its temperature fluctuations. Planck satellite measurements show CMB temperature variations of about 1 part in 100,000 across the sky. These variations arose from density fluctuations in the early universe. The pattern of fluctuations depends on several cosmological parameters, including the density of dark matter and normal matter. Dark matter affects the CMB in specific ways. 1. Acoustic peaks. The CMB power spectrum shows peaks at specific angular scales. The heights and positions of these peaks depend on the ratio of dark matter to normal matter. 2. Integrated Sachs-Wolf effect. Photons traveling through evolving gravitational potentials get redshifted or blue-shifted. Dark matter's distribution affects this. 3. Gravitational lensing of the CMB. Intervening dark matter bends CMB photons, slightly smearing the temperature pattern. This lensing can be measured and mapped. Analysis of Planck data determines dark matter density, omega m h squared, equals 0.120 plus or minus 0.001. Baryon density, omega b h squared, equals 0.0224 plus or minus 0.0001. These precise measurements match expectations from other independent observations. The CMB confirms dark matter exists and determines how much there is. Galaxies aren't randomly distributed. They form a cosmic web, filaments, walls, clusters, and voids. This structure grew from tiny density fluctuations in the early universe through gravitational instability. Denser regions attracted matter, growing denser. Underdense regions lost matter, becoming voids. Simulations of structure formation using only normal matter fail. Radiation pressure and other effects prevent normal matter from clumping efficiently in the early universe. Add dark matter, and everything changes. Dark matter doesn't interact with radiation. It clumps freely under gravity, creating potential wells where normal matter can accumulate. The Millennium simulation, one of the largest cosmological simulations, modeled structure formation in a cubic volume 2 billion light-years on a side, tracking over 10 billion particles.
Using lambda CDM parameters, including dark matter, the simulation produced a cosmic web remarkably similar to observations: filamentary structure, galaxy cluster distributions, void sizes and shapes, galaxy merger histories. Without dark matter, simulations don't match reality. With dark matter, they do. This isn't proof in the strictest sense, but it's highly suggestive. The model works because it includes the right physics, including dark matter. Einstein's general relativity predicts that mass bends space-time, deflecting light passing nearby. Gravitational lensing allows direct mapping of mass distribution, both visible and dark matter, without needing to see the matter itself. Strong lensing, massive galaxy clusters create multiple images of background galaxies, Einstein rings, or giant arcs. Detailed modeling reveals the cluster's total mass distribution. Weak lensing, subtle distortions in the shapes of millions of background galaxies, reveal underlying dark matter distribution across large areas. The Dark Energy Survey, Hyper Supreme CAM Survey, and other projects have mapped dark matter over thousands of square degrees. Results show dark matter halos surround galaxies and clusters, extending far beyond visible matter. The halos are roughly spherical or ellipsoidal, with mass decreasing with distance following specific profiles, like NWF, Navarro-Frank-White profiles. Dark matter forms filaments connecting galaxy clusters, exactly as simulations predict. Cosmic shear measurements, the overall distortion pattern from weak lensing, constrain the total amount and clustering properties of dark matter. All measurements agree with lambda CDM predictions within uncertainties. Galaxies form inside dark matter halos. Simulations show the process. 1. Dark matter collapses into halos first, before normal matter can collapse efficiently. 2. Normal matter falls into the dark matter potential wells. 3. Gas cools and condenses at halo centers. 4. Stars form from the condensed gas. 5. Galaxies grow through mergers and continued gas accretion. This framework explains why large galaxies form early, dark matter halos assemble hierarchically, allowing gas to accumulate in deep potential wells, why satellite galaxies exist, small dark matter halos orbit within larger halos, hosting satellite galaxies like the Magellanic Clouds around the Milky Way, why galaxy masses correlate with halo masses. The deeper the dark matter potential well, the more gas can accumulate, forming a more massive galaxy. And why ultra-diffuse galaxies exist. Some halos contain very little normal matter relative to their dark matter content, creating faint, extended galaxies. Observations from Hubble, JWST, and ground-based surveys confirm these predictions. Galaxy properties correlate with inferred dark matter halo properties in ways the model predicts. Empirical relationships connect galaxy properties in ways that dark matter explains naturally. Tully-Fisher relation, spiral galaxies. A galaxy's rotation velocity correlates tightly with its luminosity. Faster rotation means more luminous galaxy. Faber-Jackson relation, elliptical galaxies. Stellar velocity dispersion correlates with luminosity. Both relations follow from the connection between dark matter halo mass and galaxy stellar mass. More massive halos have deeper potential wells, higher velocities, and typically more stars. The scatter in these relations is small, a few tenths of a dex. This tight correlation across thousands of galaxies of all sizes suggests an underlying physical connection mediated by dark matter halos. Modified gravity theories struggle to explain why these relations are so tight and universal.
The Milky Way has dozens of satellite dwarf galaxies. Andromeda has even more. Many of these dwarfs are extremely dark matter dominated. Segway 1, a Milky Way satellite, has a mass-to-light ratio exceeding 1,000 in solar units. It's almost entirely dark matter. These dwarf galaxies test dark matter theory because they're simple, small, isolated, lacking complex baryonic physics that complicates larger galaxies. Observations match predictions for key properties. Number of satellites. Lambda CDM predicts hundreds of small halos around Milky Way mass galaxies. Many contain too little normal matter to form visible galaxies, but some do. The observed count of 60 satellites is consistent. Spatial distribution. Satellites aren't randomly distributed. They concentrate along the cosmic web filaments that fed the Milky Way's growth. Observations confirm this anisotropy. Velocity dispersion. Dwarf galaxy internal velocities indicate dark matter halo masses matching predictions. There's tension, the missing satellites problem and too big to fail problem, but these likely reflect incomplete understanding of how galaxies form in small halos, not fundamental failure of dark matter theory. If dark matter consists of particles, they might occasionally annihilate with each other, producing gamma rays, neutrinos, or other detectable products. Several tantalizing hints have emerged. The galactic center excess. Fermi Gamma Ray Space Telescope detected excess gamma rays from the Milky Way center with energy spectrum potentially matching dark matter annihilation. However, this signal could also come from unresolved millisecond pulsars. The interpretation remains ambiguous. The AMS O2 positron excess. The alpha magnetic spectrometer on the ISS measured more positrons at high energies than expected from cosmic ray interactions. Dark matter annihilation could produce positrons, but so could pulsars. Again, ambiguous. Neutrino signals. IceCube at the South Pole searches for neutrinos from dark matter annihilation in the Sun or galactic center. So far, no confirmed detections, only upper limits. These indirect searches constrain dark matter properties. If dark matter annihilates, it does so at low rates, suggesting weak interactions or high masses. No smoking gun yet. Particle physics offers several candidates. Bold, WIMPs, weakly interacting massive particles. For decades, the leading candidate, WIMPs would have masses 10 to 1,000 times the proton mass and interact via the weak nuclear force. Conveniently, particles with weak force interaction strengths and 100 GeV masses naturally produce the right dark matter density in the early universe, the WIMP miracle. Candidates include neutralinos, supersymmetric partners of normal particles, Kaluza-Klein particles from extra dimensions, and other BSM, beyond standard model, particles. Experiments have searched for WIMPs through direct detection, underground detectors waiting for WIMP collisions, indirect detection, looking for WIMP annihilation products, and collider production, the LHC creating WIMPs. After 40 years, no confirmed detection, WIMP parameter space is increasingly constrained. Axions. Hypothetical particles proposed to solve the strong CP problem in quantum chromodynamics. Axions would be extremely light,
10 to the minus 5 to 10 to the minus 2 electron volts, and very weakly interacting, they'd behave like a wave rather than discrete particles. Experiments search for axions by converting them to photons in strong magnetic fields, ADMX, haystack. Still no detection, but vast parameter space remains unexplored. Sterile neutrinos. Hypothetical neutrinos that don't interact via weak force, only through gravity and possibly mixing with ordinary neutrinos. Masses could range from keV to GeV scale. Different mass ranges have different astrophysical implications. Some X-ray observations hinted at sterile neutrino decay signals, but interpretations are controversial. Primordial black holes. Black holes formed in the early universe from density fluctuations, not stellar collapse. If abundant enough, they could constitute dark matter. Constraints from microlensing, CMB, and other observations limit their contribution, but certain mass ranges remain viable. Exotic alternatives: dark photons, self-interacting dark matter, fuzzy dark matter, ultralight bosons, asymmetric dark matter, Q-balls, and more. The variety reflects our ignorance. We don't know what dark matter is.
Why is dark matter so hard to detect? Weak interactions. By definition, dark matter interacts weakly, if at all, with normal matter. Trillions of dark matter particles pass through your body every second without touching a single atom. Low collision rates. Even the most sensitive detectors, tons of ultra-pure material deep underground, expect maybe a few dark matter collisions per year. Background noise. Cosmic rays, radioactive decays, and other processes create signals that mimic dark matter. Distinguishing signal from background requires extreme care. Unknown properties. We don't know dark matter's mass, interaction cross-section, or coupling to normal matter. Experiments must search across wide parameter spaces. Current direct detection experiments include LUXZ ZEPLI, LUXZ, 7 tons of liquid xenon, 1.5 kilometers underground in South Dakota, looking for nuclear recoils from WIMP collisions. XENONT, 8 tons of liquid xenon, underground in Gran Sasso, Italy. Panda X4T, 4 tons of liquid xenon, underground in China. SUPERCDMS, using cryogenic detectors cooled to about 10 millikelvin, sensitive to very low mass WIMPs. These experiments have ruled out large swaths of WIMP parameter space. If WIMPs exist and interact as theorized, we should have detected them by now. The null results push theory toward lower masses, harder to detect, weaker interactions, even harder to detect, and alternative dark matter models requiring different detection strategies. The lack of WIMP detections, combined with null results from the LHC searching for supersymmetry, has created a crisis. WIMPs were attractive because 1. They naturally produce the right relic density, 2. Supersymmetry predicts them, 3. They're detectable with feasible technology. But nature has not cooperated. Some physicists argue we should broaden the search. Lighter dark matter, sub-GeV, heavier dark matter, multi-TeV, strongly interacting dark matter, non-particle dark matter, fields, waves. Others suggest dark matter might be completely inaccessible to detection, only revealing itself through gravity. This would be disappointing, but not impossible. If dark matter interacts only gravitationally, we might never identify it directly, only infer its presence through gravitational effects. The field is at a crossroads. Continue WIMP searches, pivot to alternatives, develop entirely new detection strategies. The search for dark matter continues with increasingly sophisticated experiments. Darwin, Dark Matter WIMP Search with Liquid Xenon, proposed 50-ton liquid xenon detector 10 times larger than current experiments, could definitively test remaining WIMP parameter space. XLZD. It proposed collaboration combining LZ and XENON-T expertise for an ultimate xenon detector. Super CDMS SNOLAB. Upgraded Super CDMS optimized for low-mass dark matter installed in SNOLAB, Canada's underground laboratory. ADMX EFR. Extended frequency range. Expanded axion search covering broader mass ranges. SKA. Square Kilometer Array. Although primarily a radio telescope, SKA will search for dark matter effects on pulsar timing and hydrogen gas dynamics in galaxies. Cosmic ray experiments. AMS-02 continues measuring antimatter and cosmic rays on the ISS. DAMPE, CALET, and HERD. Space-based detectors searching for dark matter annihilation products. HLLC upgrades. High luminosity LLC will collect 10 times more collision data, potentially revealing dark matter production in rare processes. Even without particle detection, astrophysical observations will continue revealing dark matter's properties. LSST, Vera Rubin Observatory, beginning 2025, will survey the entire southern sky repeatedly, measuring gravitational lensing with unprecedented precision, galaxy distributions testing dark matter clustering, dwarf galaxy satellites in the local universe. Euclid Space Telescope, ESA's mission to map cosmic structure across 10 billion light-years using weak gravitational lensing, galaxy clustering, and baryon acoustic oscillations. Roman Space Telescope, NASA's Wide Field Infrared Telescope, will complement Euclid, mapping dark matter through lensing and galaxy surveys. CMB-S4, next-generation ground-based CMB experiment, will measure gravitational lensing of the CMB with exquisite precision, constraints on dark matter interactions in the early universe, and the sum of neutrino masses related to dark sector physics. 21-centimeter cosmology. Radio observations of neutral hydrogen in the early universe might reveal dark matter interactions affecting the first stars and galaxies. These missions will constrain dark matter's distribution, clustering properties, and interactions, even if we can't detect it directly. Detecting dark matter would be one of the greatest scientific achievements in history. If we detect a dark matter particle, we'd determine its mass, its interaction cross-sections, whether it's its own antiparticle, its production mechanism in the early universe. This would confirm physics beyond the standard model, potentially validate supersymmetry or other theoretical frameworks, open new areas of particle physics, connect particle physics to cosmology in concrete ways. If we conclusively rule out WIMPs, we'd redirect searches toward ultralight axions and axion-like particles, primordial black holes, sterile neutrinos, completely unexpected candidates. Either outcome advances knowledge. Null results aren't failures, they're constraints that guide theory. If detection remains elusive,
we might conclude dark matter is essentially invisible beyond gravitational effects. We'd study it through precision gravitational measurements, simulations and theory, indirect inferences from cosmic structure. We'd know dark matter exists, but accept we might never directly touch it. Recent breakthroughs in machine learning, quantum sensors, and detector technologies provide hope. Experiments impossible a decade ago are now feasible. The search will continue. Despite overwhelming evidence, some physicists question whether dark matter exists at all. Could all observations be explained by modified gravity instead? Arguments for modified gravity: eliminates need for undetected particles, explains galactic rotation curves with one simple modification, philosophically simpler, Occam's razor. Arguments against: can't explain bullet cluster observations, separation of mass from light, fails to match CMB anisotropies without additional assumptions, struggles with large-scale structure formation, and requires different modifications at different scales, not a unified theory. Most physicists favor dark matter because it provides a unified explanation for all observations. Modified gravity requires case-by-case explanations. But the question remains legitimate. Until we detect dark matter directly, alternative explanations deserve consideration. Suppose centuries pass without dark matter detection. Scenario 1. It's there, but inaccessible. Dark matter interacts only gravitationally. No amount of experimental sophistication will detect it because there's nothing to detect beyond gravity. We'd study dark matter through gravitational effects exclusively. Lensing surveys mapping its distribution, simulations predicting its behavior, inference from cosmic structure. We'd know it's there, but never touch it. Scenario 2. We're looking in the wrong way. Dark matter exists, but has properties we haven't considered. Detection requires technologies or approaches not yet invented. Historical example, neutrinos were proposed in 1930, but not detected until 1956, 26 years later. Dark matter might require similar patience and creativity. Scenario 3. Our understanding is incomplete. Maybe dark matter is more complex than a single particle species. Perhaps there's a dark sector, an entire zoo of dark particles with their own forces and interactions, disconnected from normal matter except through gravity. This hidden sector could be as rich and complex as the standard model, yet completely invisible to us. Scenario 4. Something fundamental is wrong. Perhaps gravity behaves differently than general relativity predicts at cosmic scales, or quantum mechanics needs revision, or our understanding of the early universe is flawed. This seems unlikely given how well current theories work, but science must remain open to paradigm shifts. Dark matter forces confrontation with deep questions. The nature of existence. 85% of matter in the universe is fundamentally unknown to us. We live in a cosmos where the vast majority of substance is invisible, intangible, beyond our senses. This challenges intuitions about reality. What we see is not what's there. Appearances deceive on cosmic scales. The limits of knowledge. Can humans understand the universe if its main constituents are inaccessible? Dark matter might be fundamentally undetectable except through gravity. If so, there are hard limits to empirical science. Some truths might be inferential only, never directly observable. The anthropic question. Dark matter is necessary for galaxy formation. Without it, structure wouldn't have formed, stars wouldn't exist, and you wouldn't be here to contemplate it.
why does the universe have dark matter in precisely the amount needed for structure formation? Coincidence? Anthropic selection? Deeper principle? The humility lesson. For most of human history, we thought the visible universe was all that existed. Dark matter reveals cosmic humility. We know almost nothing about the universe's contents. Normal matter, atoms, light, everything we interact with, is a tiny fraction of cosmic material. This should inspire both wonder and caution. How much else have we missed?
Decades of observations have proven dark matter exists. Galactic rotation curves, cluster dynamics, gravitational lensing, cosmic microwave background anisotropies, large-scale structure, all require dark matter. The evidence is overwhelming. Dark matter is real, but we don't know what it is. WIMPs, axions, sterile neutrinos, primordial black holes all remain possibilities. 40 years of searching has ruled out some candidates and constrained others, but detection remains elusive. This might seem like failure. It's not. Science advances through constraints. Every null result narrows possibilities. Every experiment refines our understanding of what dark matter isn't, even if we don't yet know what it is. The search continues with unprecedented sophistication. Next-generation detectors, space missions, and theoretical frameworks are pushing deeper into parameter space. Within decades, we might detect dark matter directly and identify its nature. Or we might conclusively rule out WIMPs and pivot to alternatives. Either way, we'll learn. And even if dark matter remains forever inaccessible beyond its gravitational signature, we'll continue studying it through the structures it creates, the galaxies, clusters, and cosmic web that define our universe. Dark matter shaped cosmic history. It enabled galaxy formation. It created the conditions for stars, planets, and ultimately life. We owe our existence to something we've never seen. That's humbling and profound. The universe is mostly invisible. The mysteries outnumber the answers, and humanity's quest to understand the cosmos continues, driven by curiosity about the vast darkness that holds everything together. Dark matter reminds us there is more to reality than meets the eye. Much more.